Good morning, everybody. This is a continuation in our course on statistical computing and machine learning. This is Professor Nicolas Zabaras, and today we will deviate a little bit from the review of different probability distributions that we have seen in earlier lectures and introduce some fundamental theorems in probability. So we will start with a brief overview of one or two basic probability inequalities that can be useful in practice. We'll talk about the law of large numbers and the Central Limit Theorem. And then we will try to relate all of this with some simple ideas from Monte Carlo or sample-based methods, such as, for example, doing integration using samples with our theory completely based on the Central Limit Theorem. All right, so let's briefly review the topic. So we will talk about the Markov and Chebyshev inequalities. We will refer to the law of large numbers and the Central Limit Theorem. I'm going to give you a Monte Carlo approximation for distributions, an example of estimating pi, accuracy of Monte Carlo approximation and how you can bring the error of approximations based on samples below some threshold. I'm going to do an example to show you that the binomial distribution can be approximated as a Gaussian. I'm going to do the same thing approximating the Poisson distribution as a Gaussian, and both of these results will be based on the Central Limit Theorem. And then I will give you one example of using the Central Limit Theorem to control, if you like, the level of noise in signals. Okay, so the goals for today's lecture are to learn a few fundamental inequalities in probability and understand the laws of large numbers and also the Central Limit Theorem. I want you to learn how to use the CLT to do statistical approximations, and certainly I will give you an example, as I mentioned, on integration. We will see an example of approximating the Poisson distribution with a Gaussian, and finally I am going to bring in, since we're going to be talking approximation of distributions with Gaussians, sort of a first look at what is called the Kullback-Leibler KL distance measure between distributions. So this will be a measure that can tell us how one probability distribution is close to another. So it will be a useful thing, for example, to show how the Poisson distribution approximates a Gaussian for different values of the parameters. All right, so let me start with the basic, a few inequalities from probability theory. These inequalities are very simple to evaluate them, and actually we will do all of this discussion just in one slide. Of course, there is much more than one slide, but in one slide you will see that somehow you can get some very interesting approximations for bounding probabilities, and these approximations can have lots of practical implications, especially in modeling things such as rare events and the like. So let me start with x being a non-negative random variable, and let me take a positive number a. All right, so I'm going to prove to you that the probability that x is greater or equal to a is bounded by the expectation of x divided by a. Now, notice I haven't said what this probability, what the distribution of x is. So the implication here is the only thing I'm doing is I'm saying if x is non-negative, so if it's positive and a is a positive number, what you see there is actually valid for any probability distribution with those constraints. So let's try to prove it in one line. Remember, the definition of the expectation is the integral over the support of my distribution that I denote here as pi of x. And the integral goes from 0 to infinity because you remember making the assumption here that x is non-negative. So this integral is, because a is a positive number, is always greater or equal to the integral that you see here, where my lower limit in my integration is a. And because the x inside the integral is positive and it's always greater than a, so I can actually write this integral as being greater or equal to a times the integral of pi of x dx from a to infinity. And you remember the integral of pi of x dx from a to infinity is nothing else but the probability of x being greater or equal to a, and that leads to the first equation, which is known as the Markov inequality. I'm going to try to demonstrate various forms of this inequality so you can get some sense of potentially how it can be used and what exactly it means. All right, so so what I'm going to do is, if the inequality as written for a random variable x that is non-negative also can be applied for any function of the random variable x that satisfies the same constraints. So in principle, I can write the equation that you see here on the bottom, that the probability of f of x being greater or equal to a is less than the expectation of f of x divided by a. And so I'm going to make certain choices for f of x, and again with the assumption that the values I have are non-negative and a is positive. So let me use f of x being this square of x minus the expectation of x, and substitute this f of x inside my Markov inequality in the middle of the slide. So we're going to get the following. I am going to first I'm going to simply change variables, and instead of a, I'm going to use epsilon square. So here I have the probability of f of x greater or equal to a. So I have the probability of this greater or equal to epsilon square, which is equivalent to actually saying the probability of the absolute value of x minus e of x greater or equal to epsilon. Again, like alpha epsilon is a positive number here. And the expectation of f of x is nothing else but the variance of x, which I am writing here as sigma square. And a, I took it as epsilon square, so this is a new inequality. So if you look at it and you try to say with words what this inequality means, it basically tells you that the probability that you are away by epsilon from the mean of the distribution is bounded by sigma square over epsilon square. And if you actually want to make it even more practical, instead of epsilon, you can reparameterize this and use, instead of epsilon, put epsilon times sigma, and actually rewrite this inequality as the probability of x minus the expectation of x being greater than epsilon sigma. And if you put here epsilon sigma in the denominator, sigma square and sigma square cancel, and you get 1 over epsilon square. So again, the probability of being away from the mean by a distance epsilon sigma, where sigma is the standard deviation of the distribution, is always less or equal to 1 over epsilon square. You can plug in, as an example, epsilon to be 2 here, and you can immediately see that the probability of being away from the mean by 2 times sigma is always less or equal to 1/4. I mean, if you think about it, this is an amazing result, because it doesn't say anything what the distribution is. It doesn't say I work with Gaussians or anything like that. I use only the fact that, x is a non-negative random variable, and with an expectation that exists, and more or less nothing else in the derivation that goes on this slide. So you can use this and figure out what's the probability of being certain distances away from the mean, and this is, in this case, again bounded with 1 over epsilon square. If you check in the literature, you will find many different inequalities similar to the ones that you see here. And the only message that I want to pass along is you have to be careful don't be very excited when you see these inequalities, because if we look, we go to our first Markov inequality on the top, right? If we see that this probability is bounded from above by E of x over A, right? So you like this E of x over A to be as small as possible, because if somebody tells you that the probability of x greater than or equal to A is less or equal than, let's say, 25, you say thank you very much, because I already know it's less or equal to 1. So you expect to have bounds that they are tied, so these inequalities can become useful in practice. So some of those inequalities that you will see in the literature, if you try to use them, there is no guarantee that those bounds that you will get will be tied, which means a lot of research is going to make these bounds as tight as possible. So if you can lower these bounds for these probabilities, even by a small percentage, that is considered a significant advancement in this area, because again, these inequalities are very useful in practice. Okay, so that's all about inequalities. So we discussed about the Markov inequality, and I gave you also the Chebyshev inequalities that they are listed on the bottom of the slide. So let me move on and provide you a rapid review of the law of large numbers. So let's consider that we have xi samples or random variables that they're drawn independently from a distribution that has some mean mu and some variance sigma square. So considering these samples as random variables themselves, the expectation of xi is mu and the variance of xi is sigma square. I am not telling you anything what the underlying distribution is, so it can be anything, and the only thing here is that they come from some distribution, that they have a mean mu and a variance sigma square. So I introduced in an earlier lecture the sample mean that you see defined here again. So if you take the expectation of the sample mean, and you will see that the expectation, remember that xi's are independent, so when you compute the expectation, of course you don't have a problem, so the expectation of E of xn would be 1 over n, the summation of the expectation of each xi, which is mu, so you actually get that the expectation of the sample mean is mu. I can do the same thing with the variance of each of these terms, and each of these terms is 1 over n times xi. So the variance will be the sum of the variances, and what I get is I get sigma square over n. So the expectation of the sample mean and the expectation of the variance of the sample mean are given as mu and sigma square over n respectively. So let me state, with all of this given now, let me state the weak law of large numbers. The weak law of large numbers takes the following form. It says that as n goes to infinity, the probability of being away by a distance epsilon from the mean is equal to 0 for every epsilon that's positive. In other ways, if you give me an epsilon, I can make n sufficient large so that this probability that you see there becomes equal to 0. Okay? So effectively you get a sense by looking at the weak law of large numbers that the sample mean, asymptotically in the context of probability, approaches the true mean of the distribution. And let me put the statement for the strong law of large numbers. The strong law of large numbers, it's actually not only written down in the context of a probability, but it is written down that asymptotically, as n goes to infinity, the sample mean almost surely is equal to the true mean of the distribution. So in essence, in practical terms, this means that with probability 1, the sample mean, so x1 plus x2 plus xn divided by n converges to the true mean of the distribution. So this is extremely important. So if you want to approximate if you want to find an estimate of the mean of a distribution using samples, you can actually take the sample mean, and you know, as n goes to infinity, either in probability or in the limit that you see with the strong law of large numbers, xn converges to the true mean of the distribution. All right, so in essence, we can use these laws to infer the parameters, in this case, the mean of the distribution. But in general, maybe we should be able to use similar ideas, not only to compute from samples what mean is, but also the variance. So the bigger problem where you estimate the parameters of a distribution from data, it is a typical problem in statistical inference, where somebody gives you a bunch of data coming from some underlying distribution, and I make this data here being vectors in Rn, and maybe you make some assumption what the distribution will be, and we call this the parametric problem. So maybe you assume that it's a multivariate Gaussian, and the parametric problem is to compute the mean and the variance of that multivariate, let's say Gaussian, by using the data D that you see on the top. The non-parametric problem that we will not consider today, it doesn't assume any distribution, so we don't have any parameters, and it is more or less an exploration of the relations between the data in your data set. So this numerical exploration problem is of course very much relevant in a lot of machine learning applications, but I will leave this for discussion later in the course. For now, I want to concentrate on this parametric problem, that effectively you have a distribution that you want it to explain the data, and the idea is to use the data to compute the parameters of that distribution, similarly to what we did with the law of large numbers. So let me do a specific example. Let's say that we have this data that there are vectors in R2, and we want to fit them with some two-dimensional Gaussian. So we want to compute the mean and the variance of this Gaussian. That's our main unknowns. I remind you, the PDF of the distribution looks like this in 2 dimensions. And so we want to compute x0, and we want to compute sigma. Obviously, I already told you that x0 is a good approximation from the law of large numbers, is the sample mean. Okay. Now, I can more or less do a similar approximation using the law of large numbers for the covariance. And so let's follow the definition of the covariance, right? So it says here, this is the expectation of x minus e of x times x minus e of x transpose. So here, if I look inside the expectation, this e of x, we already said we can approximate it with a sample mean, right? With a sample mean. Now, if you think about it, I said before that I have samples, x1, x2, etc., coming from this Gaussian distribution. So effectively, I also have samples of this function that you see inside this expectation. So I can use the idea, to be able to approximate the expectation with the sample mean, right? I require that my samples are IID, but if I take functions of my samples, f of x1 and f of x2 and f of x3 for any function, those samples will also be IID. So effectively, if you consider here this expression within the expectation, you can approximate this with a sample mean, and you see the expression written exactly here, following exactly the law of large numbers. Okay? So effectively what I'm using here is I'm using samples xj minus the sample mean times xj minus the sample mean transpose. So I have n of those samples, and this is an approximation of the expectation that you see. So the equation that is written on the bottom defines the sample covariance or the empirical covariance metrics, if you like. And I will only point to something that you need to pay attention as we move forward in the course. There are two approximations here, right? One is the Monte Carlo approximation with this summation, this averaging over the samples. But the other approximation that is involved inside this covariance is we needed to approximate the expectation of x. And because we don't know the true expectation of x, we took another approximation within this approximation on the bottom, that the expectation of x can be approximated with the sample mean coming from data. Okay, so this is again the empirical mean and variance, you can call them sample mean and sample variance. Okay, they're all the same for what we're interested in this course. Okay, so let me talk briefly about a little bit of a stronger and more interesting theorem going beyond what the law of large numbers. And I'm going to go directly to the equation on the bottom of the slide. So I am going to start with defining the sample mean exactly as before. And I'm going to state what the central limit theorem says. It says that as n goes to infinity, the sample mean actually follows from a Gaussian distribution with mean, the true mean of the distribution from where I got the samples, and a variance that is sigma square over n, where sigma square is the variance of the distribution from where the samples xj came from. So let me repeat again, the sample mean basically follows a Gaussian distribution with mean mu and variance sigma square over n, and this happens as n goes to infinity, so for large n. And I remind you, my original data x1, x2, xn, etc. don't come from a Gaussian distribution, can be from any distribution that has a mean mu and a variance sigma square. But if you take the sample mean, then the sample mean follows a Gaussian distribution. I mean, before we show with the law of large numbers that the sample mean approaches in probability and in strong form the true mean of the distribution, but now we see that as n goes to infinity, the way that the sample mean approaches the mu is with an error, if you like, or a variance that's of the order of sigma square over n. So as n goes to infinity, this variance here goes to 0, and this Gaussian distribution becomes a delta function around mu. But why we care even more about this theorem? Because if n is not going to infinity and you want to have some approximation of the error in approximating mu is actually going to be defined by sigma square over n. Okay, and we will use this in applications. Now, if you want to normalize the sample mean, I'm going to give you another statement that maybe it's a little bit heavier heavier notation, if you like. If you take a new random variable, so if you subtract from xn the true mean and you divide it by the standard deviation of this distribution, which is sigma over square root of n, then this new variable zn follows a standard normal random variable. All right, and you see the PDF of that variable. So you can use it in this form, or if you want it in normalized form, x bar n minus mu over this standard deviation follows a Gaussian n with mean 0 and standard deviation 1. Okay, obviously you can make a connection of this, and we will see in examples that the central limit theorem has a lot of applications, right? So for example, when you use models and you try to introduce some noise in the model, you always should introduce additive noise. And the idea here is, so not only actually you introduce additive noise, but the noise that you introduce that way, you take it to be Gaussian. And the idea is directly related with what you see from the central limit theorem. So if you add a lot of these random variables, regardless of what distribution they're coming from, they're following a Gaussian distribution. So let me give you a few schematics with examples. So what I have here is I have samples from a uniform distribution, and I form the sample mean, and then I take a histogram of the sample mean. So if I only use one sample, obviously the distribution is nothing else but a uniform distribution. But if you use two samples, you can see it starts looking like a Gaussian, and if you use n equal to 10, the sample mean actually follows a Gaussian distribution quite well. Remember, the emphasis here is the samples for the that I use to produce this Gaussian on the right hand side are basically samples that they're coming from a uniform distribution, all right? A uniform distribution. So if you take 10 of those samples in forming the sample mean, that sample mean follows a Gaussian distribution. And here is another example where now my samples come from a beta distribution. And you know, if you take, let's say, a sample empirical mean with 10 samples, you can see the distribution looks very close to a Gaussian distribution. So all of these are outcome of the central limit theorem. So I mentioned before that the central limit theorem, it is a little bit more useful than the law of large numbers because it can tell us something about the error that we do when we approximate the true mean of a distribution with the empirical mean. And let me give you an equation that makes that clear. So you remember the sample mean, and I'm writing it here as mu bar, right? When I put a bar, I will be implying here my sample mean. So the sample mean follows a Gaussian with a true mean as a mean and a variance that is sigma square over n, where that variance is approximated by the empirical variance. So you remember, if I have a Gaussian distribution, so mu bar follows a Gaussian distribution, I can define the 95% central interval, and I remind you the formula that you see on the bottom. So if I am plus minus 2 times the standard deviation away from the true mean, all right, that interval gives me 0.95. So this is the variable I'm interested, okay, and you can see the interval between mu minus 196 sigma, all right, and the interval between mu plus 196 sigma. So plus minus approximately 2 times the standard deviation that I have here. That interval is the 95% probability central interval. So effectively, this 196 sigma bar over square root of n, it gives you an idea of the error that you do when you approximate the true mean with the empirical mean. And you can easily pose a question. You say, you know what, can you tell me how many samples do I need if I want to drop this error below a value epsilon? And here's the answer, right? So once you have computed your empirical standard deviation, you want this error to be less than some value epsilon. So n has to be greater than 4 times sigma square over epsilon squared, where again, this sigma bar square is your empirical variance that you compute from your samples. So again, the central limit theorem here is very useful in computing this sort of confidence intervals, and also figuring out the number of samples that you need to approximate things with samples as accurately as you wish. Okay, generally speaking, and this is sort of a very early sort of touch for our course with Monte Carlo methods, when you see calculations that they're done using samples, in general we call those Monte Carlo methods, right? And Monte Carlo methods, we will see in the course, can imply a lot of different things, but I use the word Monte Carlo here to imply anything that uses samples to do approximation. So in some sense, when I evaluate my true mean with the sample mean, that's a Monte Carlo method, right? The same thing for the variance. So let me show you a few examples of this type of Monte Carlo methods. So this is something that we already have seen. Let's say that P of X is a uniform distribution from -1 to 1, so the density is 0.5 here. And I do a transformation y equal x squared, and I want to figure out what is the PDF of y. So the way you actually do this is you draw samples from P of X, you square them, you form a histogram, and that's P of y. Okay? So you can think of this as a Monte Carlo approximation for the distribution of P of y. Again, take samples from a uniform distribution, square them, put them in a histogram form, and if you want, you can do what is called kernel density estimation. You can fit them with a nice smooth P of y, but what we see on the two pictures on the middle and the right are basically the distribution P of y produced through data. And here is another Monte Carlo approximation, and in this case I'm approximating data with a Gaussian distribution, and again I am using, so actually in this particular case we have a histogram, and then we fit this histogram with what I mentioned before, a kernel density estimation, and you notice depending on how many samples I have, the approximation that I get, this kernel density estimation gives me, in this case, an approximation that doesn't look very good versus the exact Gaussian from where the data are coming. This is the red PDF that you see, but as the number of samples increases, when I do kernel density estimation, the approximation starts getting better and better, and this is the approximation for 100 samples. I know I have not said anything yet about kernel density estimation, so think somehow on again using samples to fit a distribution, and in earlier lectures we saw how we fit things with a Gaussian, right? So if somehow I told you that this distribution is a Gaussian, you can compute the sample mean and the sample variance and then plot a Gaussian. But I believe these pictures here that you see, I am not assuming that this is a Gaussian. I am fitting a density to the samples, and as we can see, the more the samples, the better that fitting is. But I am not fitting a Gaussian by simply approximating the mean and the variance. This is what we have done in earlier lectures here. We're using kernel density estimation again to approximate the distribution from samples directly. Okay, let me do a very nice example of integration using samples and using basically the central limit theorem, if you like. And I'm going to use an example that will allow me to approximate pi. You remember your famous pi, the 3.14, etc.? So I'm going to give you a statistical method for approximating pi, and even approximating the error that you do by using Monte Carlo methods. So let's set a framework where we'll be able to do such a thing. So what you see here is a square from -2 to 2 and -2 to 2. And just for to generalize things, I am using r to be equal to 2, right? So I am gonna take two random variables x and y that are sampled uniformly in this square from -2 to 2 and -2 to 2. All right, so r is equal to 2 in this particular example. So what I'm gonna do is I'm gonna obviously you see there is a circle here, all right, and that circle has a radius of equal to 2. So I want you to start thinking of an experiment that I'm going to do. I am going to take samples of x and y that are coming from this uniform distribution of this square, and I'm going to be counting effectively how many times the samples are inside the circle that has radius 2. And you may say, why am I going to do this, right? I'm going to explain in a second, but let's not forget that our problem is to get an approximation of pi. So let me start with an integral. I am claiming here that this integral that you see here, from minus r to r and minus r to r, remember r is equal to 2 in our case, this is an indicator function, so I'm claiming that this integral is the area of the circle, which is pi r squared. Remember this indicator function, it's only equal to 1 when you're inside the circle. So effectively, what you integrate here is you integrate over the circle. So this integral with the indicator function gives you pi r squared. Then you know what I do is I multiply outside, so pi then will be I over r squared, right? So rewriting the first equation, pi is I over r squared. So what I'm doing is I multiply outside the integral with 4 times r squared, and then I divide by 1 over 2r times 1 over 2r. And you know what? Don't forget that 1 over 2r is the probability of x because it's sampled uniformly in the interval minus r to r, and another 1 over 2r is the probability of y that is also sampled uniformly from minus r to r. Okay? So outside the integral, the r squares will cancel, and pi is 4 times this integral. And you know what? I look at that integral and it says, well, where is the central limit theorem, right? That integral to me, and don't forget, by the way, x and y are independent, so I can write this even as the density of x comma y. So this integral to me, you know what it looks? It looks as the expectation, as the expected value of this indicator function. And you know what? From the law of large numbers or the central limit theorem, this expectation, right? So the true expectation of this indicator function can be approximated with samples. And I am done. So effectively what I have to do is I have to draw a number of samples n for xs and ys, okay? And remember x and y are drawn independently. Form the sample mean of the indicator function, multiply with that coefficient 4, and that's my pi, done. And if you take a good number of samples, and you may have to click this program to see how many we needed. This is again a program from the PMTK toolbox of Kevin Murphy. So if you do that, you compute what pi is, and it comes to be a very nice 3.1416 with a standard error of 0.09. And you have to trust that actually you can reduce the error to any value you wish by adjusting how many samples you actually take. So everything you know in calculus about integrals, you can evaluate those integrals with Monte Carlo methods. So if one time you have difficulties to compute an integral and you don't know what to do, remember there is always Monte Carlo. And that's a statement actually that is true for many things in statistics. If nothing works, 99.99% of the times Monte Carlo sample methods will always work. Okay, so that's an example, an application of the central limit theorem that I use here also to get the standard error. So that's an application of CLT in computing integrals, and in this particular example, evaluating pi. Let's do another example. Let me take the binomial distribution. And for those who forgot what the binomial distribution is, let me remind you, you have a coin that has probability mu to get heads and probability 1 minus mu to get tails. You are tossing the coin n times, and in those n times you get m heads, and the probability density for m follows the equation that you see on the top. So you remember that when we discussed about the binomial distribution and we did a calculation for the mean and the variance of the binomial distribution, we actually, what we did is we said that m is equal to x1 plus x2 plus xn. Remember, n is the number of heads, and these variables x1, x2, xn, if those are samples from the binomial distribution, they're actually binary variables, right? So m is equal to x1 plus x2 plus xn, all right? So this sample mean of these x's that come from a Bernoulli distribution with probability mu, they are equal, this sample mean is equal to m over n. But you remember from the central limit theorem, and it doesn't matter from what distribution x's come, the central limit theorem says that this sample mean follows, as n goes to infinity, follows a Gaussian with a mean, the true mean of these binary variables, which is mu, and a variance that is sigma square over n. And I remind you, the variance for the Bernoulli variables is mu times 1 minus mu. And from this, if you get rid of this n, you get that m follows a Gaussian distribution with mean n times mu and a variance n times mu 1 minus mu. Now, we already had shown actually that the mean and the variance of the binomial distribution are given similarly to what you see here, but we never stated before that somehow the number of heads is actually can be approximated as n goes to infinity, can be approximated as following a Gaussian distribution. All right? So now you're learning that the central limit theorem basically tells us that the binomial distribution as n goes to infinity, it's actually very close to a Gaussian distribution. And you do see here a binomial distribution with mu equal 0.25, and you can see for n equal to 10, this nice distribution, binomial distribution, looks very close to a Gaussian distribution. Again, where is that coming from? It comes from the central limit theorem. Okay, I'm going to actually show you similar result for the Poisson distribution that we have seen in an earlier lecture. And before I do this, I had promised at an earlier lecture I'm going to tell you a little bit more on the Poisson process. So let me try to spend 1 or 2 minutes to define what a Poisson process is without deriving anything. So let's say that we are counting some events, and the count is an integer number, so it's 0, 1, 2 to infinity. All right. So I'm counting the number of events in some time interval from 0 to t. So this can be, number of earthquakes in, in 50 years or something like that, or some other event. Okay, so we're counting some events, and n of t is the number of events that we observe in the interval 0 to t, and the only constraint right now is that n of t is an integer. So we're going to make, to derive what is called a Poisson process, we're going to make 3 fundamental assumptions, and if you want to read more on this, you can look on this textbook on fundamentals of probability by Garamani on page 213 on the newest version of the book. So the 3 assumptions to derive a Poisson process start as follows. The first assumption is called stationarity. So if we take 2 equal time intervals, and what I mean equal means time intervals of the same length, right? So delta 1 and delta 2 being 2 equal time intervals. Then for any non-negative integer n, all right, so n is the number of events, the following is true. The probability of observing n events in delta 1 is the probability is equal to the probability of observing n events or counting n events in delta 2. So if I have 2 equal intervals, the probability of seeing the same number of events in those 2 intervals is the same. Obviously, you can extrapolate why we call this the stationarity property. So that's property 1. Property 2 is what is called the independent increments property. So let me define it, following again the reference on the bottom. So let me take times t1, t2, tk in this order, and I'm going to define an event ai to be the event that I see ni events to take place in the interval ti to ti plus 1. So again, the notation here, the subscript I, refers to the beginning of the time interval, right? So the time interval that I'm doing observations between ti and ti plus 1. And ai is the event that I observe ni events, right? So I mentioned before the events can be earthquakes. So, so A1, for example, will be the event that I observe N1 earthquakes in the time interval T1 to T2, okay? And T1, T2, Tk, they are exactly as stated here. So this assumption of independent increments basically says that these events A1, A2, Ak minus 1 are independent, okay? And if you want me to write this in probability, if you take the joint probability of these events, then it factorizes, as we have seen for independent events, as P of A1, P of A2, P of AN. Okay, and then we have another fundamental assumption to derive the Poisson process, and this assumption goes with the name, negligible probability of coincidence, if you like, or as Garamani calls it in the textbook, orderliness. And basically it says that the probability of having 2 or more events in a very small time interval is very tiny. So let me repeat again. The probability of having, for observing more than 2 events in a very small time interval is practically 0. And if you want to be more precise, remember n of h is observing n events in the time interval h. So as h goes to 0, this probability of n being greater than 1 approaches 0 faster than h does. Okay? Another way to actually mathematically write this is if you take the ratio of this probability divided by h and you take the limit as h goes to 0, then that ratio goes to 0. The idea here is as h goes to 0, as the time interval becomes tiny, the probability of seeing 2 or more events is negligible. So if you consult those 2 pages from this textbook on the fundamentals of probability, these 3 properties, together with the assumptions that n of t counts an integer value random variable, define what is called a Poisson process, okay? A Poisson process. And let me summarize what we have said up to now. So this Poisson process, and I'm not giving you a proof, counts the number of events from 0 to time t. And here, if I take a realization of those events, so let's say when capital N becomes little n, the density of little n follows this distribution that is called the Poisson distribution. Okay? I am not giving you any any proof, but I give you a reference on the bottom. If you want, read it, and if you follow the previous slide and the 3 assumptions, then those lead to a Poisson process, and the PDF for n follows this nice form where lambda is a positive parameter that defines this Poisson process. Okay, I'm going to simplify this to define the Poisson distribution. So you will never see the Poisson distribution written like that with the time given explicitly. So when you see things with the time involved like that, this is what we call a Poisson process. So I'm going to try to simplify and bring it to the form that is familiar to most as the Poisson distribution. So what I'm going to do is I'm going to fix the time t, and I'm going to call this time to be capital T, and I'm always going to be observing the number of events happening in that time interval from 0 to capital T. Okay, and I'm going to, because I only have one time, I am going to call lambda times capital T theta, and that becomes my new parameter. So in this case, the PDF for the Poisson distribution takes a very simple form that you see on the bottom, right? So lambda capital T becomes theta to the power n divided by n factorial e to the minus theta. Okay, and I mentioned sort of the fundamental assumptions that take us from a Poisson process to the Poisson distribution that you see in this slide. So you don't have to know all of these things, right? But for today's lecture, I am going to actually, I'm not going to do a complete proof. I'm going to sort of try to bypass a tiny little proof needed in addition to what I have done now. But I'm going to show you another amazing result that based on the central limit theorem, this interesting Poisson distribution that does counts of events in a certain time interval, you know, this capital T, can be approximated rather well with a Gaussian distribution. Right? Again, there's the Gaussian distribution, and suddenly I'm saying that the Poisson distribution can be approximated with a Gaussian distribution. So let me see how we can actually show this. Before I do anything, let me summarize the formulas for the expectation and the variance of for the Poisson random variable. So both the mean and the variance come to be equal to theta. So it's very easy to remember that in the Poisson distribution, both the mean and the variance are equal to theta. Okay, that's why when you parametrically write the Poisson PDF, you only use one variable because there's only one variable, right? Both the mean and the variance are the same. Okay, so I am going to show you now that a Poisson distribution can be approximated with a Gaussian distribution, and I only need a very tiny little statement that I'm not going to prove it, but is given on this link that you see at this slide, okay? And this tiny little statement says the following: if you have a random variable x that is drawn from a Poisson distribution, then this random variable can be considered as the sum of n independent random variables xi that are drawn from the Poisson distribution with parameter theta over n. Okay? It's not very difficult to prove it, okay? But let me repeat again. If x is a sample from a Poisson distribution, you can see that sample as the sum of x1 plus x2 plus xn, where x1 and x2 all the way up to xn are drawn from a Poisson distribution but with parameter theta over n. All right? Now you can see I have samples coming from a Poisson distribution with parameter theta over n, and these samples of my original Poisson distribution are the sums of the samples. So my head already spinning and saying, wow, this maybe has something to do with the central limit theorem and this empirical mean that we used before, and that's indeed the case, right? So if you take the empirical mean of these samples, we know from the central limit theorem that they're basically draws from a Gaussian that has a mean which is the same mean as the mean of this Poisson distribution with parameter theta over n, which is, as we know, the mean is theta over n, and has a variance that is the variance of this distribution divided by n. And the variance of this distribution is theta over n. So you get a theta over n squared. So sigma of xi, which you remember is our sample x from the original Poisson distribution, then can immediately you can see from this equation from the central limit theorem that the this random variable x, all right, is drawn from a Poisson distribution, but at the same time can be considered as a drawn from a Gaussian distribution with mean. If you get rid of this n here and you put it inside the Gaussian, you will get that the summation of xi follows a Gaussian that has a mean theta and has a variance theta. You remember when you you compute variances, if you want to get rid of one of n, you're going to have to multiply by n squared. So the Gaussian that approximates our original Poisson distribution has a mean theta and a variance sigma squared, and here it is. So basically what we have what we proved here is that if x follows a Poisson distribution with parameter theta, we can very nicely approximate those samples with samples drawn from a Gaussian distribution that have a mean theta and a variance also theta. If you don't believe me that this is the case, after this proof, let me just go and do this by using different number of samples to approximate the Poisson distribution with a Gaussian. And you can see here, I suppose the dots are samples from the Poisson distribution, and the straight line, what you see is the Gaussian approximation, okay? And these plots are the values that you see here, mean equal to 5, mean equal to 10, are the parameters theta. So as I go from the top left to the top right and all the way to the bottom on the right, the parameter theta increases. So as theta increases, the approximation becomes better and better, and the Poisson distribution can be written as a Gaussian. You don't have to worry that every distribution can be approximated with Gaussian, right? But we already have seen some, like the binomial came to be a good approximation using Gaussians, and now we have the Poisson distribution also being can be very well approximated with a Gaussian. Actually, since we talk about approximating distributions, one distribution with another, I wanted to throw a new idea and definition that is going to be very handy later in the course, and that definition has to do with a measure of how close one distribution is to another distribution. And that measure is what is called the Kullback-Leibler distance, or simply called the KL distance between two densities. So one of the densities in our case was the Poisson density, and another one was the Gaussian density with the same mean and variance as the parameter theta of the Poisson distribution. So what is the KL distance between two distributions that measures the distance sort of between two distributions is given by this nice summation, because you remember the Poisson distribution is defined for integer n's, right? The Gaussian is for continuous, but here we're approximating the Poisson distribution where n is integer, so I have a summation for all possible values of n of the Poisson distribution times the log of the Poisson distribution, the Poisson density divided by the Gaussian density. I don't want to spend a lot of time to talk about the KL distance yet, right? But just keep in mind that as a distance is greater or equal to 0, and it's only equal to 0 if the two densities are the same. The distance is not symmetric, so if I take the distance of the Gaussian from the Poisson distribution, the answer is going to be different, okay? But right now, this is a measure of how well I can approximate with this Gaussian my original Poisson density. And if you compute this by plugging in the two densities that you see on the top, and you sum for all possible values of n, you actually get a plot that looks like this. And the vertical axis is the log of the KL distance, and the horizontal axis is the parameter theta of the Poisson distribution. And you can see the higher the theta, the better the approximation. And this line that you see here, again, the vertical axis is on a log scale, is the axis where the KL distance drops by 1/10 from the value that it had when the parameter theta was equal to 1. Okay, so immediately you can see that the KL distance becomes smaller and smaller, so the approximation becomes better and better as the parameter theta increases. So I want you to just remember this KL distance, because is actually going to be a fundamental measure to use, for example, when we use variational methods and we try to approximate implicit distributions with, for example, Gaussian distributions. And what I mean, implicit distributions, for example, can imply distributions either represented in terms of samples or through some computer code that allows us to evaluate samples. So again, this is the general definition of the KL distance. If the distributions, if the densities here are continuous, for continuous variables, instead of summation you will have an integral, and that's what most probably we will use. But here we have a summation because n is an integer. All right, so let me finish with one last example, another application of the central limit theorem. And this is an application to time signals that have noise on them, right? So suppose you do an experiment and you measure some quantity, let's say a current or a voltage in time, and let's say you measure this signal in n time steps, so you record the values at n time steps, and obviously that signal is corrupted with noise, okay? So the first thing I am going to do is I'm going to try to, using the law of large numbers or the central limit theorem, I'm going to try to get an approximation using one measurement. I'm going to try to get an approximation of the mean and the variance of the noise vector. So to do that, obviously you need to know what the true noise-free signal is, and what to do that, right? You're going to have to calibrate your measurement with something where you know what the true signal is without any noise. And if you know what the true signal is, you can subtract it from your noisy signal and compute a purely noise signal. Okay, so I'm going to show you, maybe if I can go back to the next slide. So noise signal may be something like what you see here, all right, over a time interval, let's say from 0 to time 50. So if you do calibrations, maybe you can get one signal that is a purely noise signal, and using that signal, we can assume that the values the noise signal takes at the different time instances are IID, and effectively we can use the central limit theorem and those values of the noise signal at the different times to compute the mean value and the variance of that signal. And that's what I have. If I can go to this, back to the previous slide, I have, so if you do calibration and you remove the true value of a signal, you're left only with noise. And if you average that noise, you can get the average noise, and you can get the standard, you can get the variance of that noise vector with only one calibration experiment. Okay? All right, so now you start doing real measurements again, and you want to be sure that because now your measurement signals are going to be corrupted by noise, you want to be sure that you have the signal to noise ratio under control, right? And so what you can do is you know, as you expect is you say, okay, if I do this measurement, let's say of current or voltage over time, from time step 0 to time step n, maybe what I can do is I can repeat this experiment 10 times or 50 times and average my measurements at each time step. All right, so if you average these signals, you are obviously averaging the noise as well, right? You don't want to go and compute the noise at each measurement that you do, but in effect you're averaging the noise over the repeats of the experiment as well. So let me take the kth experiment where you do some measurements, and let's call x little k to be the noise vector in that kth measurement. All right, so if you're going to average your noisy signals, effectively you're defining an average noise vector as well, okay, that looks like this. And obviously this is a realization from some random variable, you know, this random variable is capital XK that you see here. And the question is now, can we say something about, if we look at the different time instances, can we say something about the behavior of the average noise vector? All right, so remember here we are averaging this over different measurements. Okay, so I'm repeating the experiment multiple times, I'm averaging over n experiments. So at each time, can I say something about the mean, and also more importantly here, can I say something about the variance, the error that I have on my noise? You know, what is the level of the noise that I have when I average my measurements? And the answer is, asymptotically, the level of the noise that you have is sigma square over m. You remember, according to the Central Limit Theorem, this follows a Gaussian. And what is the Gaussian? It has a mean, the true mean of these vectors xk, and which is actually the mean that we computed from the calibration experiment. And what variance does it have? It has the true variance, which we take it to be sigma square, again from the calibration experiment, divided by n. So this averaged noise vector, or if you like, the noise vector that results from averaging my measurements, has a variance that is sigma square over n. And then you can say to yourself, you know what, how about if I want this this variance to be less than some threshold tau square? Or if you want the standard error, if you like, sigma over square root of n, to be less than tau. Well, if you do that, then you can figure out how many measurements you need to achieve that. And there is a little computer program that demonstrates this for noise signals. So I'm taking signals that have, they're defined in time intervals that they're equal to 50. For demonstration, I'll take sigma squared to be equal to 1. And I repeat the experiment once, all right? So there's no averaging here. I'm averaging here over 5 measurements, okay? Over 10 measurements, over 25 measurements, and you can see this, you know, the standard, 2 times the standard deviation of my noise, which is 2 times sigma over square root of n, becomes smaller and smaller. So you can define how much small you want this to keep the signal to noise ratio to a desirable level, and then you can from there see how many averages, how many times you have to run your experiments and average them. So this noise reduction idea for signals by averaging, again, it's a fundamental result that comes from the Central Limit Theorem. And this particular example, if you're interested, is from a very nice and very small book on Bayesian scientific computing by Calvetti and Somersallo. And it is obviously this is an example of practical significance in signal processing, and in essence it justifies the common practice of averaging signals with the objective on taking control of the signal to the true signal to noise ratio that you have in your measurements. Okay, so I am going to stop there, and we will continue next Tuesday with another lecture. Until then, see you.